Okay, good afternoon, everybody. It is indeed a pleasure for me to be speaking to you today. It was my hope a year ago that I would have actually been visiting in Medellin, and I was looking forward to that. I still have plane tickets, and so hopefully someday I will indeed be able to visit. I have not been there yet. So the title of my talk is Food Colloids and Emulsions, Principles and Applications to Dairy Products. Um, when we began this presentation, the date was March the 5th, and this is what our administration building on campus looked like at that time. It was unfortunate that we weren't able to continue that day. Um, but today, at March 24th, I'm happy to say that the snow has all gone. The green is starting to return, and we're getting closer to springtime. So here's an outline of what I will present today. Um, During the first part of the lecture, I will just review the basic principles of colloid and emulsion science, and then more specifically emulsion formation, emulsifiers per se, and emulsion stability and instability. So that first half of the presentation is just basically a sort of an in-depth overview of the field of colloids and emulsions and as they relate to food systems broadly. In the second half of the lecture, I will focus more specifically on dairy emulsions, and I've divided that into two categories. In the first instance, I'll talk about milk and creams, and primarily as examples of emulsions where we want stability and where we build in stability through processing. The second category of dairy emulsions that I'll talk about are whipping and whipped cream, and ice cream mix and ice cream. In both of those cases, we build in a controlled instability in the emulsion so that we can set up structure through the fat globules and a fat crystal and fat globule network. And so I will be contrasting stability versus instability in a controlled way by looking at those dairy emulsions. So that's what I will cover in the next hour and a bit that we have time together. And at the end, I'm certainly happy to answer any questions that anybody has. So just one moment for me there, please. I'll just move that. Okay, we'll start at the beginning and just define what we mean by a colloid. A colloid is a system. It could be a food system or other systems in which we have finely dispersed materials dispersed into a medium or the continuous phase in which they're not dissolved, but they remain dispersed as a discrete particle. So this is the colloid system that we're talking about, where we've got particles dispersed and stabilized in a continuous phase in which they're not miscible, they're not dissolved. And as a result of that, we have a free energy or an interfacial tension between those two particles. So the very first thing to recognize is that a colloid system is not an equilibrium system. It's not in thermodynamic equilibrium. And if we require stability in a colloid, we need to build in kinetic stability to prevent this movement towards an equilibrium state. So we have lots of different colloids. In the food area, we primarily talk about emulsions and foams. So emulsions can be liquid or solid particles dispersed into a liquid or a solid phase. And it may be oil, for example, dispersed in water. We would call that an oil in water emulsion. Milk is an example. Or it could be a water in oil emulsion, where the water particles are the discrete droplets dispersed in a continuous oil phase. And butter or margarine would be examples of those kinds of emulsions. We also have a lot of food foams in which we've got a gaseous phase dispersed into a liquid or a solid. And so later on, I'll talk about ice cream. Ice cream is both an emulsion and a foam, and it has both liquid and solid phases within it, so a complicated system. So these are the different kinds of colloids. Now, I want to differentiate right at the very beginning here with the term hydrocolloids, which is also frequently used. And this term was coined a number of years ago, but a hydrocolloid is not necessarily a colloidal particle. So with hydrocolloids, we're talking about water-soluble polymers, particularly those that interact with water and can swell, and as a result of that, induce viscosity or possibly gelation. Most of them are polysaccharides, non-starch, but some modified starches might also be considered as hydrocolloids, and some proteins like gelatin can be considered as hydrocolloids. But a polysaccharide dispersed in solution is not necessarily a colloid. It depends on the size of aggregate of polymers that are there. So it's just important to differentiate what we mean by colloids and what we mean by hydrocolloids. And they're really two different and separate areas of research. And we have journals and conferences related to hydrocolloids, and likewise we have journals and conferences related to colloids. My focus today will be on colloids, even though I do a lot of hydrocolloid work as well. So emulsions are colloids, and that's certainly what we're here to talk about this afternoon. So when you think about an emulsion, you have a continuous phase, you have a discrete or dispersed phase, and you have an interface in between the two. And that interface, of course, becomes incredibly important when we think about stability and instability of our emulsions. So these are just a few electron micrographic pictures of emulsions to give you the idea of the diversity of particle size, the diversity of membrane material that might be absorbed around there, and I'll look at all of those in a bit more detail as I go along. So an oil and water emulsion, for example, you can start off with oil, you can start off with water, you can stir those and agitate them and use high shear blenders and homogenizers, and you can mix the oil into the water phase, and it will be stable for a very short period of time. Thermodynamics will take over to try to minimize the surface area, minimize the free energy, and within a very short period of time, you'll get phase separation again. So emulsions are inherently unstable, and as they move towards equilibrium, they will lead to a phase separation to try to minimize the surface area. So what we need to do with emulsions is build in a kinetic stability, and that comes from the interfacial layer, from the surfactant or the surface active agent or agents, the molecular materials that become adsorbed at the surface of the droplet and stabilize the droplet from separation from that continuous phase. So the surfactants build in that kinetic stability. The emulsion is always thermodynamically unstable and inherently will move towards equilibrium. But if we build in kinetic stability, we can hold that over time in that stable state. So emulsifying agents, they need to be amphiphilic materials that will adsorb partially on the oil phase and partially on the water phase, and reduce the free energy, reduce the interfacial tension because of that amphiphilic nature that they have. And so if you have a molecule with two components to it, and one component can dissolve in one phase, the other in the other phase, then they will move to the interface and lower the interfacial tension between the two phases. We have lots of different types of surfactants, and I'm going to get into that in a little bit more detail as I go along again. Depending on the nature of the molecule, They can either exist in a very tight film around the droplet, or they can expand and extend out into the continuous phase. And the type of material in the lipid phase and the type of the material in the continuous phase, or I should say the discrete phase of the continuous phase, going to have a big bearing on the properties of those droplets. Okay, so that's just those are just some of the definitions, the basic principles of colloid and emulsion science. Now, emulsion formation generally takes place through homogenization. It's the most common food technique for creating emulsions. And the principle is that we break up the oil phase into smaller and smaller and smaller droplets, and we have enough surfactant in there to be able to cover all of the surface area that we've created. So I won't go into uh, all of the details that are presented on some of these slides. A few of these slides are rather wordy, but I have provided the PDF version of the slides to the organizers, and they will make them available to participants so you can go back and look at these to get more of the details if you wish. Just one comment from me: I would appreciate if you use these slides for your own personal use only, and that you don't share them beyond personal use without express permission from myself. I don't want to see them being used as course notes without reference back to me as the source. So at any rate, this is what the homogenization principle is all about. We apply enough external pressure to overcome the internal pressure in the droplet, and that causes the droplet to be further dispersed, and then the emulsifier that's there adsorbs to that new surface area and provides stability as a result of that. The principles I'll show you in the next couple of slides. This is a standard, this is a Tetra Pak homogenizer, food style homogenizer. It's typically just a very large, either 3 or 5 piston positive pump with a very large electric motor in order to be able to drive the fluid through the homogenizing valve with a very large pressure drop across that valve. So we need to be able to drive that fluid with a high amount of pressure through the homogenizing valve. This is just a schematic diagram of the homogenizing valve and a picture of the valve itself from a typical Tetra Pak homogenizer. So the principle is that our unhomogenized product is moving into the channel of the homogenizer, and then because of the applied pressure, we create a very, very thin gap. And as the fluid moves from the fairly large diameter of the inlet chamber to the incredibly small gap, its velocity goes up extremely high because of that constricted flow space. So in other words, there's this relationship between flow rate, diameter, and velocity. If you constrict the diameter at the same flow rate, the velocity goes up tremendously. And it's that incredibly high velocity that then causes disruption of the oil into the continuous phase, or vice versa if it was a water and oil emulsion. So you can see the principle here of disruption of droplets. The coarse emulsion goes into the homogenizing valve. As it passes across the seat of that valve under that very, very high velocity, it's the turbulence that's created and the cavitation that's created and those incredibly high shear forces that disrupt those fat globules, create more and more surface area, and then provided that we have the surfactant there to absorb onto that surface area, we can stabilize the droplets through the homogenizing valve. So that's the principle of emulsion formation. There are other kinds of equipment that the food industry uses, but by far the most important technique would be a homogenizer, a pressure homogenizer, and that's the principle of what it's trying to do. So a couple of important messages come out of that, which I'll get to next. And one is the role of pressure in terms of dispersion of the discrete phase and droplet size that's related with that. And two is the presence of the emulsifier, the surfactant, to stabilize those droplets as they are forming. So that walks right into the next portion, which is a little bit of discussion about emulsifiers that are used in the food industry. So in this slide, I asked the question, how do you view an emulsion? And as I've described it so far in point number one, an emulsion droplet is a quantity typically of oil with a surfactant around it. And there you can see oil droplets in the two micrographic images on the top. They're partially crystalline droplets, so the white streaks inside are crystals of the fat as a result of cooling of the oil to below its crystallization temperature. I'll come back to the importance of that later. But in the second instance, I suggest that the other way to picture an emulsion droplet is a, a layer of surfactant that is enveloping or enclosing the oil in the middle of it. And you can think of this as sort of an encapsulation. And why it's helpful to think of an emulsion that way is from the point of view of activity in the continuous phase, whatever any molecule in the continuous phase is going to see is a giant ball surrounded with surfactant. It's not going to see what's inside that oil droplet. So for example, if we have an enzyme, lipase enzyme, for example, the lipase enzyme can't see the triglyceride in the oil droplet if it's surrounded by protein. It just sees a very large protein ball. So it's just another way of thinking about an emulsion droplet that helps to reflect on questions like stability and activity. So in terms of thinking about a fat globule after homogenization, it could be covered with a thin layer or a heterogeneous layer of protein, as shown in the top, or it could be encapsulated within a larger kind of a protein aggregate. And in the bottom, that was created with a microfluidization process. And there you can see fat droplets that are even smaller than the protein aggregates. And as a result, they get more or less encapsulated within it. It's more like a microemulsion, or you could even view it as sort of a nano-encapsulated system. But nevertheless, it still is an emulsion in terms of the components that are in it and the way it was created. So the role of the emulsifier is to prevent particle recoalescence at the time of formation, and then to remain stable on that droplet over time to build in that kinetic stability for shelf life. So in the first instance, the role of the emulsifier is to create our droplets by stabilizing those bare surface areas that are created by the homogenizing force. And so they lower the interfacial tension, and as they adsorb, then they can stabilize that droplet. So the surface that you can create in a homogenizer is limited by the available surfactant. Or to put it another way, you can create surface, but you can't stabilize it without that surfactant being there. And I'll show you a few examples of that. Typical protein coverage might be 2 to 3 milligrams per meter squared. Now, when you think about a square meter of surface area of fat in an emulsion, if you think about the size of a meter, a square meter, 2 to 3 milligrams is like molecular thickness. So these proteins adsorb and provide a very, very thin film on the surface of a fat droplet. And our small molecule surfactants are even going to be less. They're going to be like at almost atomic measurement. And again, I'll show you an example of that when we get there. So this diagram shows, for example, the size of particles that you can form and stabilize in a homogenizer as a function of the protein that's present to stabilize them. So what you can see here is that in this range here, we have sufficient protein to stabilize the surface area that's being created. And the size of the droplet then is going to be a function of the energy input. So you want smaller droplets, you need more homogenizing pressure, for example. However, in this area, protein is limiting. So it doesn't matter how much applied pressure that you apply to the emulsion. If you create so much surface area that you don't have enough protein to absorb around it, then it's going to recoalesce almost immediately. And therefore you see this relationship between particle diameter and protein concentration that shows this limiting amount of protein and then limiting pressure input and the relationship between the two. And that's shown again here. This diagram on the left is a diagram that came from work from Professor Valster in the Netherlands from several years ago. But what it shows on the y-axis is particle diameter, so on a log scale, and on the x-axis is homogenizing pressure. And you can see this relationship, this linear relationship between particle size and homogenizing pressure. However, what's also shown here is that this is the volume fraction of oil that is present. And as the volume fraction of oil goes up, the particle size is going to go up at any given pressure. And why would that be? Well, because this was done at constant protein concentration. And so as you get more oil and smaller droplets, then you become limiting in protein or limiting in surfactant to stabilize that. And that means that there's going to be immediate recoalescence, and your particle diameter is a function then of your protein available to stabilize it. So proteins, when they adsorb to interfaces, they're fairly large molecules, of course. And when they adsorb to interfaces, they're going to rearrange at that interface in order to come to some kind of a lowest free energy state based on the hydrophobicity and the hydrophobic patches within that particular protein and its ability to sort of unfold some of those tertiary bonds and rearrange. So you do get a bit of an interfacial denaturation and rearrangement of a protein molecule so that it's moving its hydrophobic regions towards the oil phase and its hydrophilic regions towards the water phase. And as a result of that, you may get a substantial amount of the protein extending away from the surface of the droplet into the aqueous phase, and that can confer a tremendous stability to protein-stabilized emulsions. So we often refer to that as steric stabilization because that refers to the portions of the molecule that are extending away from the interface and the interaction then of those portions of the molecules with other droplets that may come in close proximity. So things like we talk about sometimes loops and tails that stick out. These, if you think of this as the oil phase and the water phase, with a highly structured protein, you may get a very high hydrophilic component that may extend away from the interface. And if it can completely unfold, you may get something that would give you a much thinner interface. As we get increasing protein concentration, they do have the ability to pack and to lead to higher protein concentration until such time as you saturate the surface, and that would be that maximum protein concentration per surface area of droplet. So all levels of protein structure are involved because we need hydrophobic regions. We also need enough flexibility within primarily the tertiary structure so that we can unfold that protein and drive those hydrophobic regions to the interface. And then the hydrophilic region becomes involved because that's the stabilizing layer. So things like surface charge of the hydrophilic region, that steric layer, how much of it is sticking away from the interface, those are all the kinds of things that are going to predict whether a protein will be a good emulsifier or not. And some are, and some are not. The caseins, I'll come to them later when we start talking about dairy emulsions. They are notoriously very good emulsifying agents. And the caseins pack into a casein micelle at the individual molecule level. They're known as sort of naturally unfolded protein molecules, or molecules that don't have a whole lot of tertiary structure and not even a lot of secondary structure in some cases. So if you look here at, this is alpha S1 casein and beta casein, which are the two major casein components in milk, you see a little bit of alpha helix, but not very much structure at all. Now, alpha S2 has a little bit more alpha helical structure in the protein, but there's not a lot of alpha S2 in milk. So these are naturally sort of unfolded proteins. They have large hydrophobic regions, and they have regions that are quite highly charged. And as a result of that, the hydrophobic regions can absorb and stabilize the surface, and the charged regions can act as really good stabilizing layers out into that aqueous phase. All those casein molecules get packed into a casein micelle in nature, and they do so through calcium phosphate. It's nature's way of carrying high levels of calcium to the neonate of mammalian species. So there's a very good reason why calcium interacts with phosphorine residues in the molecules, and that's the way of carrying calcium, and because of its biological role in nature, which is to feed the infant mammals. But of course, that means that we've got this highly bioavailable calcium available in human nutrition as well. But anyway, I'm not getting into nutrition at all today. The focus is really on the physical properties of these proteins in terms of colloids and emulsions. So this is structurally what a casein micelle would look like. When you look at it under an electron microscope, it's got this kind of a raspberry-like, sort of a heterogeneous structure of dense regions and less dense regions. And from a modeling point of view, we interpret that as the dense regions surrounding the calcium and the less dense regions where those calcium phosphate nanoclusters, protein nanoclusters, are interacting with each other. And so it has a fairly high volume and a fairly high water content within this protein aggregate. So I'll come back to the casein micelles a bit later. This is a good place to show this diagram, or this, sorry, it's not a diagram, it's an electron micrographic image. But the black areas here are casein micelles, and these are fat globules after homogenization. And you can see how even the casein micelle can kind of spread and unfold and expose the deep hydrophobic regions towards the fat globule, and that's how they absorb and stick there. And then the rest of the casein micelle can extend off of the surface of the fat droplet and help to stabilize that outer layer. And that's what I mentioned earlier, that what a molecule out here in the aqueous phase sees, or in the continuous phase of the emulsion, is this very large protein ball, and not necessarily the triglyceride within it. Now, whey proteins, they behave quite differently at fat interfaces. They are a much more typical folded globular protein. So a lot of regions of secondary structure, alpha helix and some beta sheet and beta turn regions, but tertiary structure as well through disulfide bonding. Um, and what needs to happen for a whey protein to be a good emulsifier, besides homogenization and so on, is heat to cause enough partial denaturation of your whey protein to expose some of that inner hydrophobicity, to allow it to absorb and stabilize onto a fat droplet. And similar to many other plant proteins that we could describe as well, soy proteins can be okay surfactants. Now there's a lot of interest in some of the legume proteins, like pea protein, for example, is demonstrating itself to be a reasonably good emulsion surfactant. And some of the highly purified pea proteins being extracted now and available in a cleaned up and fairly concentrated form. So proteins, in summary, provide dense adsorb layers. Oftentimes the layer is charged. Especially if you've got a region that's highly negatively charged, for example, that can extend off the surface, and that then gives your emulsion droplet a net negative surface charge, which gives you repulsion stability, and that's a positive thing as well. The layer can be extended from the surface, and that gives you that steric stabilization property. You may have a high viscoelasticity. Once you get the squeezing of the protein onto the interface, then that provides quite a lot of stability through the viscoelastic property at the interface. So charge, steric, and mechanical effects. So great surfactants in terms of stability. There are many other types of emulsifiers as well. Phospholipids, and I'll touch on these fairly quickly and without spending as much time. But phospholipids, as demonstrated there, it's similar to a triglyceride in that it's got a diglyceride structure, i.e. two fatty acids, but the other carbon moiety here is through an ester bond to a phosphate group, and the phosphate group could be choline, ethanolamine, serine, and so on. So phosphatidylcholine, phosphatidylethanolamine, these are the natural phospholipids that are present in things like milk fat and like the lecithins, the plant or vegetable lecithins. So soy lecithin, for example, fairly high in phospholipid. Their emulsifying activity is not as good as some of the other small molecule surfactants, and typically they're not really purified. So when you buy a soy lecithin, the actual phospholipid content can be fairly low, but there is a lot of more purified sort of phospholipids available now. So they can be natural emulsifiers in the milieu of other proteins and so on, but not necessarily real good emulsifiers in their extracted state. The small molecule surfactants are the things like monoglycerides, or a whole bunch of chemically synthesized small molecule surfactants, the lactic acid esters, the lactams, propylene glycol esters, the diacetyl tartaric acid esters, the datums, sucrose esters, and then the spans and tweens. So all of these are sort of chemically synthesized to have a hydrophobic region, typically a fatty acid, and then a hydrophilic region. So in the case of a monoglyceride, if you take glycerol and reesterify that with triglycerides, you can get monoglyceride. And the one monoglyceride, which is this one here, is the one that's most functional as an emulsifier, because you've got the fatty acid residue that is the hydrophobic component, and then you've got the two carbons of the glycerol molecule here that become the hydrophilic component. So the head, if you like, of this monoglyceride molecule. But you can see that if this molecule is what's adsorbing to create an interface, then the only thing in the aqueous phase is the two carbons and their respective hydroxyl groups. So that's what I said earlier. It's almost at the atomic absorption level to give you that hydrophilic surface. So good emulsifying agents, but an incredibly thin membrane, and as a result of that, not nearly as strong and stable as what a protein stabilized emulsion would be. So then we have emulsifiers based on glycerol and emulsifiers based on sorbitan. With sorbitan, like the spans and tweens, it's basically a glucose molecule that becomes the head, emulsifier head group, the hydrophilic group. So a little bit larger head group compared to the glycerol, but still small relative to all of the components of a protein, all the peptide segments that would exist there if it was a protein as a surfactant. Now, polysaccharides, they play a role in emulsions, but typically as a hydrocolloid. So in that case, you're getting emulsion stability, but it's from viscosity in the aqueous phase rather than interfacial properties. Sometimes they say polysaccharides have interfacial properties, but quite often if they do, it's because there's a minor protein component that's associated with it. So if it's a pure polysaccharide, its emulsion stabilizing property is typically because of viscosity in the continuous phase rather than interfacial property. So we do call them emulsion stabilizers, but we need to recognize why they're stabilizing, and that's quite different than an emulsifier per se. Gum arabic would be an exception because it's got a protein component covalently linked to it in a complex. And so gum arabic makes a great emulsion stabilizer for things like low pH flavor emulsions, flavor oils, and so on. You get a very, very large hydrophilic component and then the hydrophobic component from the protein part of the gum arabic complex. Okay, so now I'll move into emulsion stability and instability. As a general statement, successful food colloids must be stable over the required lifetime of the product. Now, we need to define that because homogenized milk might be a couple of weeks, 2 or 3 weeks. But if we're making something like a Bailey's Irish Cream, for example, it might be a year, and it might be a year under ambient temperature conditions. Likewise, a lot of our coffee creams and cake icings and those sorts of products, some of them might be frozen. Some of them might be refrigerated, but oftentimes we want shelf life of several months for those products as well. So what we're doing to stabilize a food system is building in that kinetic stability over time. Now, what are the destabilizing forces? There's several of them, and what we need to think about is which ones are present in our food system and what is the sum of all of them together. And typically when we talk about colloidal stability, we're comparing the stabilizing factors versus the unstabilizing factors, and which one is going to win out and how long is it going to take. So the forces acting on colloidal particles, um, Brownian motion is certainly one. There's thermal activity within any system. So we can measure things like diffusion coefficients to give us an idea of how much Brownian motion or how much thermal movement that a particle might have. Then we've got van der Waals attraction forces that are always present. We've got electrostatic forces, as I alluded to that already. We've got the surface charge that exists on the surface, and we can measure that with things like zeta potential or electrophoretic mobility when we look at the surface charge of a particle and how it opposes other particles that have similar charges. We have hydrophobic interactions occurring, and this is because of the interaction between the head group of the emulsifying material and water. And so, if there is the ability to cause a dehydration and bring particles together, you will get hydrophobic interactions occurring as a result of that. Then we have this steric stabilizing, the interpenetration and reactions of those interfacial layers as they come close together. That's another component that's there. So the mechanical and the electrical charge, those all have to do with our colloidal stability. So the thickness, composition of the interfacial layer, those are the critical components. There are three main types of destabilizing mechanisms. One would be creaming, in which, because of the density difference typically between the discrete phase and the continuous phase, over time, the lighter phase might rise to the top. So in an oil in water emulsion, you might get the oil droplets creaming over time. We do have some food ingredients that are sometimes referred to as weighting ingredients, where their sole role in an emulsion is to increase the density of the dispersed phase. And that limits creaming because the density difference, which is the driving force for creaming, is reduced. If there's no density difference between them, then there will be no driving force for a gravitational separation. The second mechanism is flocculation. In this case, the droplets, the colloidal droplets, have come together, but they haven't lost their individual identity. So they've come together as loose flocks or as clusters. And I'll show you some of the different mechanisms that may be involved in flocculation. And the third mechanism is an irreversible one, and that's coalescence. And that would be a mechanism in which two of our emulsion droplets or our colloidal particles touch together and then fuse. And as they fuse, they typically rearrange. I didn't mention that earlier, but emulsion droplets are almost always spherical because that minimizes the surface area per volume of that droplet. So if two droplets touched and fused, they would rearrange very, very quickly to another larger round droplet. So flocculation can be reversible. Coalescence typically is irreversible. So that's again shown here that flocculation, because it leads to a larger mass, if you like, can drive creaming. And both creaming and flocculation can in fact drive coalescence. And then as we get either flocculation or coalescence occurring, that enhances creaming. So these destabilizing factors can all be interrelated, and sometimes it's hard to separate out why we might be getting a cream layer on an emulsion. What is the driving factor? Is it flocculation or coalescence? Or is it creaming? And oftentimes, light scattering, the master sizer, is the best way to try to sort out how has the particle size of the original emulsion shifted over time. In other words, flocculation can be easily dispersed, and then we can recover our particle size. Coalescence can't. And so with the use of some judicial techniques and light scattering, we can often sort out those destabilizing mechanisms. With bridging flocculation, we get a sharing of the surfactant layer. This is not going to happen with a monoglyceride, but it may very well happen with a protein or a solid particle, in which case the particle is large enough that it can absorb to more than one droplet at the same time. So here are examples where if we have particle stabilization, what's often referred to as Pickering stabilization of an emulsion by particles, then those particles might be shared between two droplets. If we have a large protein or a protein aggregate, such as a casein micelle, it could be shared between two droplets. And the other way that we can get bridging flocculation is if two of the head groups of emulsifiers interact with each other. And that could also be through bridging, for example, where we would have two negatively charged groups of proteins interacting through a divalent cation bridge. So calcium, for example, might cross-link two negatively charged proteins to cause a flocculation within an emulsion. So homogenized milk and cream would be examples, or charged polysaccharides or charged proteins. Those would be examples of bridging, where it is the polymer that's acting to hold the droplets together. Now, in this case, the two droplets aren't physically touching each other. They are cemented together by that interfacial layer. Depletion flocculation is another mechanism. It's kind of a complicated mechanism, but it happens when we get large colloidal particles like polysaccharides in an emulsion. So here you can see emulsion droplets and fairly large polysaccharide molecules together in water. And what happens is that the water moves as a result of chemical potential. And so you get these gaps, if you like, where the polysaccharide molecule cannot any longer fit between the two emulsion droplets. It's just too big. And this creates these exclusion zones so that we start getting a macroscopic phase separation between our colloidal particles and our polysaccharide, and that just drives those two phases closer together. So this is what we refer to as depletion flocculation. And so you can demonstrate it quite easily with a 10% emulsion, 10 to 20% emulsion, in which you throw 1% polysaccharide, and you're doing that to stabilize it through viscosity, but in fact, it has the opposite effect and causes an instability to occur. So there's an electron micrographic image of a destabilized emulsion through flocculation. Coalescence is irreversible. In this case, you have touching of the internal components of the emulsion droplet through a weak interface and a rupture in the interface. So there's a picture of coalescence. In this case now, your emulsion droplets are much, much larger than they were to begin with. So that destabilizing force over time has caused your particle size to increase as a result of weak interfaces and collision and touching and fusing of the internal components. So to avoid instability, with creaming, we want emulsions with small droplets and thick adsorb layers to reduce density differences. And sometimes we, as I mentioned, we can even add ingredients to the oil phase to increase the density of the oil phase. And then high viscosity of the water phase. There's the old traditional Stokes law, which shows the relationships between these things in terms of particle movement, and viscosity is in the diameter. So the higher the viscosity, the lower the rate of movement of the particle. But not too much, of course, because of the textural impact of the polysaccharide on the emulsion system. With flocculation, we want to keep those particles apart from each other and not lead to those flocks. So repulsive interactions, highly charged, extended interfacial structures, those will keep the droplets far enough apart that they won't form those weak flocks. And then with coalescence, a high elasticity and complete coverage of that adsorbed interfacial layer. So there's not any areas where you've got thin coverage that may lead to touching and fusing of the internal material. Okay, that's the first half of the presentation, and that brings me around to just about keeping in touch with my time. Um, so the second half of the presentation now is going to focus on dairy emulsions. And as I mentioned, I want to talk about dairy emulsions where we build instability, and then dairy emulsions where we promote instability. So to demonstrate a lot of the principles of the colloid science that I spoke about already. So if you're not interested in dairy systems, nevertheless, what I'm going to talk about will reinforce, I hope, the principles of colloid stability and be more broadly related to food stability of all colloidal systems. So that's my milk and my glass half full and half empty to suggest that it's time for just a very quick break. I'm going to stand up and walk around my chair and take a little glass of water and give myself a couple of minutes to regroup. And so don't run away, but everybody can take a moment now also to stand up and stretch if they like. And refill your tea or whatever you do at mid-afternoon and just give me a couple of minutes and I will reconvene momentarily. One of the things that I have observed since I have mostly started teaching remotely um, is that in my lecturing style in the classroom, I tend to be very animated, and you may have seen that already with my hands. But that means that I tend to walk around a little bit, which is good. It keeps the audience excited, but it also keeps me kind of stretched out a little bit. When I have to sit in front of a computer screen and I sit for 2 hours without standing up, I get kind of stiff. And so it's a good opportunity for me here while I'm making a presentation just to stand up and move around a little bit. Okay, I think I'm ready to carry on, so we'll stay on time and I'll leave lots of time for questions here. So I'll carry on for about 40 minutes or so and then leave time for discussion within our 2-hour time slot. All right, for those of you who are not very familiar with dairy systems, these are the important materials that are found in milk. And those are the fat globules, the casein micelles, and then the materials in the aqueous phase, which are the whey proteins and the lactose and other dissolved materials. So about 4% of milk, raw milk, typical cow milk, would be fat globules, and these are typically 1 to 10 micrometers in size. The fat globule, the natural milk fat globule membrane comes from the secretory cell. The casein micelles, they make up about 2.6% of milk, and they are also colloidal particles. Casein micelles are in that colloidal particle range. They are typically 50 to 500 nanometers in size, and they include protein, calcium, and water primarily. In the aqueous phase surrounding the casein micelles and the fat globules, we have about 0.7% whey protein or serum protein. And these are small soluble globular proteins, 3 to 4 nanometers in size. And then we have the lactose, disaccharide dissolved in water, and other minerals that are present in that soluble phase as well. So milk structure, if you look at a glass of milk, it's just an opaque liquid, but it's scattering light, and that implies that there are particles present. If you look at it under a light microscope at 1,000 times magnification, you start seeing the fat globules. And if you look at it under an electron microscope at 10,000 magnification, then you start seeing the casein micelles. And it's interesting to note that if you take all the fat globules away from milk and create skim milk, it's also white. And that's because, again, you've got a colloidal particle in there, the casein micelle, that's scattering light. If you take the casein micelles away, as in whey from cheese making, it's no longer white. So the fat globules in raw milk, a range of sizes, about 90% of them are in that 1 to 8 micrometer range. And there you can see in the lower case, they've been colorized. So you can see the range of fat droplets there in raw milk. We also have a population of very, very, very small droplets. So if you look at a number distribution, a large percentage of them are very, very small. But if you look at a weight distribution, then most of them are in that 1 to 8 micrometer size range. The native milk fat globule membrane is made up of protein, and these would largely be membrane proteins, and then phospholipids and other fatty acids and other material that might be associated there with that fat globule membrane. And it's about 8 to 10 nanometers in thickness. So a typical sort of a protein and phospholipid stabilized droplet. Now, raw milk is not very stable, and it will cream off very quickly. And it creams off for a couple of reasons. One is the larger size droplets, but two, the second reason is the fact that you've got such a range of sizes. So as the big ones rise in raw milk, they then flocculate with all these little ones, and the flock keeps getting bigger and bigger as it moves and continues to flocculate with smaller droplets because the bigger ones are moving at a faster rate. So it's that combination of of rising of the large droplets and that flocculation because of the wide size distribution that leads to rapid creaming. So we homogenize milk in order to create a stable emulsion and then be able to sell fluid milk with a shelf life of 2 to 3 weeks or much longer if it's UHT sterilized. So homogenization, it reduces the average diameter of globules, it reduces the width of the size distribution, it greatly increases the surface area, as we talked about earlier, because of all the smaller sizes. And so then you get absorption of the other serum proteins and casein micelles to the surface of the droplet to help stabilize all that new surface area that's created in the homogenizer. And the absorption of further protein on the droplet increases the density of the droplet. So it's a combination of stabilizing the surface of the droplet with added protein and increasing the density that leads to stability of the homogenized milk. So smaller diameter, more uniform size distribution, and more dense. And that's shown in this little schematic diagram, unhomogenized milk. After 1 hour, a combination of flocculation and creaming, maybe even some coalescence, and you'll get the formation of a cream layer. With homogenization, you get a stable emulsion because these droplets are more or less the same size. They are heavier. And, pardon me?
Por favor, que aparentemente tenemos un pequeño problema técnico. Cheers.
Am I okay? I heard somebody speaking. Am I okay? Yes?
Professor, can you continue with the presentation? No problem.
Okay, thank you very much. I just wasn't, I thought I heard somebody speak and I wasn't sure if somebody was trying to tell me something.
Okay.
So what our homogenized milk system does then is give us that stability because of the principles of colloidal science that I had referred to earlier. So again, you see that in this diagram where you've got parts of the original fat globule membrane, but not enough of it now to stabilize all that new surface area. So you get absorption of casein micelles and absorption of non-micellar casein and whey proteins, particularly dependent on how high that you've heated this emulsion. The heating causes more absorption of the whey protein as they unfold and stabilize and interact to some extent with the casein micelles. So this is how we stabilize our homogenized milk. With 3.2% protein in a 4% fat emulsion, we have plenty of protein there to stabilize the surface. But just remember that thought when I get to speaking about creams. So here you can see in a light microscopic picture, raw milk, as I showed you earlier, those population of very large droplets. Homogenized milk, they are all now very uniform in particle size and considerably smaller. And when you look at electron micrographic images of homogenized milk, you can see the interfacial layers around them. So here you can see the casein micelles, and you can see that monolayer coverage of protein that might be there. But the point is, with all of these droplets that you're looking at, you see this black layer around the surface of the droplet. So the entire surface of the droplet has been stabilized by adsorbed amphiphilic material, which was stained black in this electron microscopy technique. If the entire droplet surface wasn't covered, that would lead to regions where you would get very, very fast recoalescence. Now, quite often we cool milk emulsions, and as we cool them, the internal component, then the triglyceride, can crystallize. And so quite often, when you look at refrigerated dairy emulsions, you'll see extensive crystallization in the internal component of the triglyceride fat droplet. And I'll come back to the importance of that in a moment as well. So you see schematically, you've got these fat globules with casein micelles, non-micellar casein and whey proteins, and some of the original fat globule membrane material that is now stabilizing the fat globule. If we think about some of the other protein fractions that we could use in making things, for example, like reconstituted milk from skim milk powder and anhydrous milk fat or butter, when we reconstitute and homogenize in the presence of a protein extract, the composition of the protein in that protein extract is going to have a big bearing on the surface droplet and hence the stability of the fat droplet. So if we make recombined milk or reconstituted milk by homogenizing butter in skim milk powder, we're going to have something that looks very much like the original droplet that would be from homogenized milk. But that depends in part on the heat treatment of the skim milk powder during its manufacture. So you can see here in the top right that we have fairly large casein micelles, and though they're fairly large and much more heterogeneous, because in the production of the skim milk powder, they have interacted with whey proteins to some extent, and you get these aggregates, whey protein casein micelle aggregates. So reconstituted skim milk powder will form a good emulsifying layer, but the low heat powder would be better than the high heat powder so that we avoid some of these aggregates. And we get a more uniform surface coverage. Sodium caseinate is a very good stabilizing layer. It's thin relative to casein micelles, but it's homogeneous and gives us close packing. And as a result of that, a high sort of a viscosity in that interfacial layer. So sodium caseinate can make certainly a very good emulsifying layer in an emulsion. Whey protein concentrate will also do the same, but it gives a very, very thin layer that may not be nearly as stable as a sodium caseinate would be. So not all dairy proteins are created the same, of course, as we talked about earlier, and it depends on how that protein has been treated during the extraction that can affect then how it might behave as an emulsifier. So light scattering is so important in terms of being able to determine what we've done to an emulsion. Here you can see the raw milk with this large shoulder of large droplets, with homogenized milk now smaller and more uniform, and we've gotten rid of these large tails. So certainly light scattering is an incredibly important technique when we look at emulsions and emulsion stability. Now with creams, we take milk, as I've shown here on the left, we centrifuge that. That's going to cause the fat to become concentrated in a reduced volume, and that all those fat globules in that reduced volume of aqueous phase is what we refer to as cream, and the aqueous phase which is devoid of fat globules is what we call skim milk. So just simple centrifugation will separate cream from skim. The principle is to put that in a centrifugal field where we are exposing it to those centrifugal forces that tends to drive the fat at a much higher rate, the fat droplets at a much higher rate upwards, and the heavier aqueous phase downwards. So we put that through a stack of discs, and the fat droplets move upward in the discs and get separated out with a reduced volume of skim milk into the cream layer, into the cream fraction. And what's devoid of fat globules now gets separated out into the blue there, the skim fraction. So this is what a large industrial separator would look like, and what the separating discs would look like in a stack of discs. So that stack of discs is how the fat gets separated out from the skim phase. So the stabilization of homogenized cream now is going to depend on the phase volume of fat that's in the cream and the amount of protein that's there, because we can very soon get into a situation where protein becomes limiting. And if protein becomes limiting, as I've showed you earlier, you're either going to get recoalescence very quickly within the homogenizing valve itself, or you're going to get bridging flocculation. And both of those would lead to instability. So as soon as we start getting up into the range of emulsions where we have, greater than 20% oil phase, then we have to start becoming concerned about having sufficient protein to stabilize that. So added sodium caseinate, very efficient emulsifier, gives us that thin but strong stabilizing layer. Skim milk powder will also work, and then all the other plant based proteins become sort of less in their ability to form good emulsions. I showed you this slide earlier where your size is affected by both the energy input at the homogenizer and the surfactant layer, and that becomes, or the surfactant composition, concentration, that becomes more and more important as we get into higher fat emulsions. So we can calculate that required protein concentration based on the emulsion surface area, based on the energy input, of course, and we're going to get that information from light scattering, and then the protein load per surface area that we would expect for caseinate or skim milk powder and so on. So it's a very quick calculation to show you how much protein that you might need to stabilize all of the surface area that you want to create based on the size of the droplet and the type and composition of protein that you have present. And if there's not enough, that's going to lead to either recoalescence or bridging flocculation, either of which are going to lead to instability and the formation of fat plugs over time. And so stabilizing your creams become more critical than stabilizing milk, just simply because of the higher fat phase volume that's there. Now, I want to also show you as two great examples of dairy systems, whipping and whipped cream, and then ice cream mix and ice cream. And these are complicated systems because we want to induce a controlled level of instability that's going to lead to a formation of a fat globule network. And it's the fat globule network that conveys the structure to whipped cream and the colloidal structure to ice cream. Both of these are also foams. We've incorporated air into them by whipping, and the fat plays an incredibly important role at stabilizing the air interface. And so that also builds up for us fat structure, fat network structure. So both very complicated systems and great ways of demonstrating all these colloidal principles that I've referred to through the afternoon. So whipped cream, I hope many of you will be familiar with the concept. We take a heavy cream, typically 35% fat, that's just come from a high concentration through the cream separator. So the heavy cream here is in the form of a liquid. We pour that into a vessel and we put our beater in there. The beater is agitating it, which is creating shear, and it's also incorporating air. And within typically less than a minute of beating, you can see here that we've created this spoonable, stiff material that has a built-in structure to it. And that's spoonable. We can put a spoon of it on top of a dessert. I often demonstrate that in doing a little demonstration of food science. And I ask people after I've whipped that, where did the water go? It was a liquid system before, and now it's no longer a liquid system. It's a stiff spoonable system. Where did the water go? The water obviously is still there, but now it's trapped and held into some kind of a gel-like network. And in the case of the cream, it's a fat globule network that's created that gel-like system. And I'll show you some images of that. Ice cream is very, very similar in that we have a high fat content, we whip air into it, and we do so under whipping and agitation and high shear. And the stability of that ice cream system then is in part related to the absorption of fat onto the air interfaces and the clustering of fat to create, again, a fat crystal and fat globule network. And I'll show you more details on both of these systems. The key to both of these systems is what we call partial coalescence. And partial coalescence sets up for us these fat globule networks. The first important parameter to induce partial coalescence is to have a partially crystalline emulsion. So an emulsion that, for example, with milk fat, that we have cooled down, or a saturated fat like coconut oil or palm kernel oil, that we've cooled down and held sufficiently long that the droplets of fat have induced nucleation and crystallization within them and have a crystalline network in the droplet. Then, as a result of agitation and aeration, those droplets collide together, but it's the presence of the crystalline network within them that helps them retain their shape and their individual identity. If the two globules collided together in a shear field and it was liquid oil in the droplets, they would just simply coalesce into a larger droplet. You can't make whipped cream or ice cream using something like soy oil or corn oil at ambient temperature. As you whip it, the fat simply coalesces and will separate out. So the crystalline network is in there to give you structure within your droplet. Then the shearing and aeration, they cause the droplets to come together and what would have caused coalescence, but they can't coalesce because of that crystal network, and that's why we refer to it as partial coalescence. So it's somewhere in between a coalesced system and a flocculated system, but it's partially coalesced and trapped in to create those clusters as a result of the crystalline network within the droplet. Here you can see examples. On the left is just a schematic diagram of a cluster that might form. The middle is an electron micrographic image of partially coalesced fat globules. You can see the crystals within those globules, and it's pretty easy to see that you would have had several globules here that are now partially coalesce together into a cluster. And that cluster is going to form structure for us. And again, you can see that on the right as well, where two globules have collided, but not coalesced because of the crystals inside the globules. So the key to partial coalescence is temperature and the composition of the triglyceride such that you get roughly 70% of the triglycerides in the crystalline state, but you still have some liquid oil, and that liquid oil is going to help create that cementing agent to hold the globules together, but the crystalline phase maintains their shape and identity. So that's why that solid liquid ratio in the emulsion droplet at the temperature of whipping is critical for getting real good structuring in a whipped topping or whipped cream product or in an ice cream or frozen dessert type product. So now we have to recognize the solid, if we use non-dairy fat, we have to recognize the saturated fat level and the solid liquid fat ratio, and then the optimal temperature for whipping. You could see a crystal inside that droplet that's led to protrusion and weakening of that droplet, and that's going to lead to more coalescence. So this is a little schematic diagram, I hope, that puts these concepts together. You start with an emulsion droplet, and you've got a membrane around that droplet, and that could be comprised here of protein and or small molecules. You cool the emulsion droplets and you hold them for sufficient time to allow crystallization to occur within those droplets. And then the whipping causes the colliding of the droplets and the sticking together of the droplets, but the retention of their identity so that you can create a network from them. If you have too much liquid oil, they'll coalesce, and you can't create structure with coalesced droplets. If you have too much solid fat, you don't have that same liquid oil that acts to hold them together, and you just get solid fat particles that tend to bounce off each other, if you like, and not create as much structure neither. You have the added complexity of whipping air into these emulsions, and as you whip air into an emulsion, the fat will naturally try to come to the air interface, again to reduce the interfacial tension of the droplet, because your fat and water don't like to be together, nor do air and water. So the fat is more comfortable moving to the air interface and sitting at the air interface, and this is what leads to partial stability of the air droplets, of the air bubbles. So with cream, we have the combination of the coverage of the air bubble with fat and the linking of one air bubble to another air bubble through that partially coalesced fat droplet network. So come back to my question, where is the water? The water is still here, the serum phase. It's just trapped and held within this fat globule network, which is a continuous network now that will exist throughout the whole of the whipped cream product. So you can see that microstructure here. These are air bubbles here and here in whipped cream. You can see the fat globule layer all the way around the air bubble. And you can also see a lot of coalesced fat droplets that link those air bubbles together and build up those networks. And this is how we get a stiff, spoonable product from whipped cream. And it doesn't have to be dairy fat. There's lots and lots of these whipped toppings made by all of the major food companies. Some of them are sold where the consumer whips them. Some of them are sold as a whipped fresh product, and some of them are sold as a whipped frozen product. But all of them rely on partial coalescence, so saturated fat, and the temperature of whipping to develop that structure. Now, ice cream, and again, when I talk about ice cream, I could refer to products made with milk fat or to frozen desserts made with non-dairy fats, but all of the same principles apply. So if you look at an ice cream mix over here, we've got our fat droplets. They are partially crystalline because we've cooled them and held them cold for sufficient time to allow those crystals to form. We have our protein, which could be casein micelles, and perhaps non-micellar casein and whey protein. Um, and then we have added emulsifiers, and I'll talk about the importance of those in a moment. But those are dispersed in the aqueous phase, which also in the case of an ice cream mix contains a lot of sugar. Now, the whipping has the added complexity of freezing at the same time. So we're whipping air into the system as we did with whipped cream, but we're also taking away solvent out of the system by freezing it, and that is concentrating the fat in the unfrozen phase. So the 3D fat network that forms is forming as a result now of really three factors. One would be the presence of the air, and two would be the agitation, as I referred to earlier. But three is the concentration that's occurring because of the formation of ice. So we've thrown in another whole complicating system and another colloidal particle in the sense that ice could be considered, because it's a crystal, could be considered a colloidal particle in that system. So now looking at ice cream, this is an air bubble in ice cream with fat droplets absorbed around the surface of the air bubble, and they're helping to coat and stabilize those air bubbles because of that interfacial tension or the free energy associated with them moving out of the aqueous phase. There you can see a close-up of those fat droplets sitting quite happily halfway in and halfway out of that air interface. One of the key differences between ice cream and whipped cream is the fat phase volume. With whipped cream, we have about 35% fat, and we do not homogenize those fat globules so that we've got that native milk fat globule membrane around the droplet. With ice cream, we have only about 10%, 10 maybe up to as high as 15% fat in there, so much less fat. But it's also been homogenized to give us more globules to make them smaller and make them spread out more. But as a result of homogenizing, as I referred to earlier, you get the absorption of protein on there and the stabilization of your fat droplets by adsorbed protein. So with ice cream mix, you've got a very stable emulsion because of the high protein concentration. But we don't want that high level of stability. We want some instability so that we can whip that and get fat clusters forming. So in ice cream, we add small molecule surfactants, typically monoglyceride, or lecithin from egg yolk. And what does that egg yolk, phospholipid, and protein do, or the monoglyceride? It reduces the interfacial tension further than the milk proteins do. So the milk proteins over time are displaced off of the interface of the fat globule. That's happening during the aging period of the ice cream mix, as well as crystallization of the triglycerides. But now we're getting a monoglyceride layer on here. And again, as I referred to earlier, it's a very, very thin interface compared to the bulky interface formed by proteins. The implication of this is that when we agitate these fat globules in the shear field, and as a result of aeration, they will bounce off each other, but now we have greater opportunity for fat-fat interactions rather than protein-protein interactions if that fat droplet was totally coated with protein. And again, relating back to what I said in the first half of the lecture, we can think of fat globules from the point of view of the aqueous phase as just a big protein ball. So if there are these two large protein balls that collide off each other, there's nothing that causes them to stick because the outside surface is stabilized sterically by quite a thick layer of protein. So that's really the primary goal of the emulsifier in an ice cream system, to displace protein, give us a thin interface which is stable quiescently, but will destabilize under the agitation and coalescence that we get during whipping and agitation in an ice cream freezer. So you can see here, after aging, we get displacement of that protein layer, and we get the formation of thin interfaces. And you can see that here with transmission electron microscopy. So your fat droplet with adsorbed casein, no emulsifier, but as soon as you add like a monoglyceride, or in this case a polysorbate 80, which is one of those sorbitan emulsifiers, now you have complete displacement of protein from there and a much thinner interface, which is much more likely then to stick together during the collisions in whipping and freezing. So then in ice cream, this is an air bubble, and now you can see fat globules adsorbed along the surface of the air bubble to stabilize it. But you also can see these fat globule networks that are extending away from the air bubble that are going to lead to a strong sort of network in the unfrozen phase around the air bubbles and around the fat globules. So again, going back to light scattering, with ice cream, we've created this large tail or shoulder, if you like, of partially coalesced droplets. And it's these that lead to networks that lead to a holdup or a structure in the ice cream. And one of the main ramifications of that is that the ice cream will melt much more slowly as it's being consumed. So this is an example of that. If you take ice cream from the freezer and just set it at ambient temperature and allow it to melt, with no fat structuring in there, as the ice crystals melt, the ice cream is just going to drip. As soon as you have some level of fat structuring in there, you have more hold up or more shape retention and a reduced rate of melting or meltdown. When I talk about meltdown there, I'm referring really to the dripping rate. The ice crystals in all three pictures are melting at the same rate. That's just a function of heat transfer. But as the ice crystals melt, we have this secondary structure of fat that holds the whole thing together and gives you a much slower rate of dripping and melting. So I hope then by talking about whipped cream and by talking about ice cream, it demonstrates how all these principles of colloidal science and emulsion science come together and how important those interfacial layers are. So we really have to understand all aspects of the colloidal system. The fat droplets and their size and their internal composition, the composition of the outside interfacial layer, the phase volume, and how it all comes together to create either stability in a colloidal system or undesired instability, or in the case of whipped cream and ice cream, planned instability or desirable instability. So that ends the formal part of my presentation. I hope it's been interesting and informative and maybe a bit entertaining. And so I'm going to stop at this point and leave the rest of the available time for any questions and discussion. And feel free to ask questions about any topic related to, even remotely related to what I've just talked about. I'm happy to talk about colloids or hydrocolloids or share any insights I might have on any problems that you've got. So I'll stop my screen sharing and turn it back over to our moderator, who can open it up for any questions.
Thank you very much for this excellent presentation. It's a very comprehensive presentation about colloids and their applications in dairy science. It was very interesting. Right now we have one question by Carla Enciso. She asks that when you make an oily water emulsion with carbohydrates, such as maltodextrin, which moment is advised to add these carbohydrates? What effect would it have if you add the carbohydrates after the homogenization process? Could it be detrimental to the stability of the emulsion, or it would not affect the stability, or what would be its influence?
Okay. So the first comment that I'd make is that the carbohydrate itself is not going to act as an emulsifier at all. So you would need to have some emulsifier present, either a protein or a small molecule type emulsifier present. A carbohydrate like maltodextrin would not have any interfacial properties per se. What it would do is increase the viscosity of the aqueous phase, and that is going to affect emulsion stability a little bit, but not nearly as much as the primary emulsifier. So if given that you've got a primary emulsifier there and that you've created an emulsion, then if the question is, at what point would we add the maltodextrin, it would not affect the homogenizing itself, provided that you've got enough emulsifier there, unless you had so much maltodextrin that it really increased viscosity. But provided that it was a normal level of maltodextrin, it could be added before or after homogenization, and it should not necessarily affect stability of the emulsion. My caveat to most of these, though, is to say that most of these systems are complex systems, and quite often when you look at the intricacies of them, then you end up going to say, well, it depends on whether you've got this component present or another component present, and temperature and so on. So but normally speaking, for most systems, I would say that it wouldn't matter if the maltodextrin was added before or after homogenization, provided that A, it's not too high, and B, that you've got another emulsifying component present.
Thank you very much, Professor. There's another question. They asked me that first it was mentioned that there are two types of stability, a thermodynamic stability and a kinetic stability. Um, is it possible for an emulsifier to achieve both types of stability, or we will need two different molecules to achieve a kinetic and a thermodynamic stability?
So the answer is yes, that one emulsifier is going, or your emulsifying agent, if it was protein or monoglyceride, for example, would give you both some level of thermodynamic stability and some level of kinetic stability. And what I mean by that is that your emulsifier is going to reduce the interfacial tension, and that reduces the free energy of the system. So that does give you some thermodynamic stability, but remember always that complete stability from a thermodynamic point of view is completely minimizing the free energy, and you can't do that in an emulsion system. So you can lower the interfacial tension, you can lower the interfacial free energy, but you can't minimize it completely, or you would end up with a phase separated system. So that's then the role of kinetics, to slow down that movement towards equilibrium, perhaps even stop that movement towards equilibrium and trap it in that non-equilibrium state. And that's what we mean by the kinetics. The kinetics are going to refer to the rate, or the shelf life, if you like, the rate of instability. And so emulsifiers are going to do both for you. Some will depends on what they're each doing. So a small molecule surfactant like a monoglyceride, for example, is going to give you more thermodynamic stability because it'll lower the interfacial free energy further, but it's not going to be as stable over a longer period of time. So a protein would be more kinetically stable, but thermodynamically less stable. So I would say that it's you have to look at the stabilizing mechanism and then ask the question, what do we need to accomplish given our food product? And quite often, of course, it's a combination of both small molecule surfactants and proteins that give you the best stability.
Thank you very much, Professor. I have another question. When in dairy technology, what's the normal amount of pressures used in the high pressure homogenization process? When they homogenize different compounds?
Yeah. So typically, less than 200 megapascals, more would be in the range of 150 to 180 megapascals. There is interest in going to much higher pressures than that. And this area of high pressure homogenization is a real sort of interesting, both industrially relevant and research hot topic, to try to create very, very tiny emulsion droplets. That requires greater attention to the emulsifying material. And it's certainly worth noting that it takes a very high electrical energy and hence costly to run homogenizers at high pressure. And so it's certainly more energy intensive to do that. So there is also research at the industrial level to try to go to lower pressures to save electrical energy. And a good example of that are these new homogenizing valves that they refer to, for example, as microgap or stacked edge valves, where you can get the same homogenizing effect with much lower pressure to save cost and to save electrical energy. So the conventional pressure was about 100 80 megapascals, but there are movements, depending on what you're trying to accomplish, in either direction. One would be just to save energy to go to lower pressure. The other would be to try to induce new structures, new fat structures, by going to very, very high pressure.
Thank you very much, Professor. They are asking me if you consider that nanocellulose, such as cellulose nanofibrils and cellulose nanocrystals, would be good candidates to emulsify dairy products.
And I would say you will be you will be more qualified to answer that than I will. In that case, you are really talking about something like a Pickering stabilization mechanism, a stabilization mechanism as a result of another particle. Those are not typical emulsifiers in that they don't adsorb and spread on a oil water interface the way that a protein or a monoglyceride would. So yes, they can act as emulsion stabilizers, but it's a different stabilizing technique than what you would get with a protein or a conventional emulsifier.
Thank you very much. I have a question. Well, actually, I have two questions. One is that when you use small molecule emulsifiers, they tend to absorb to this fat structure, as you mentioned. And then we have a lot of proteins surrounding this fat droplet. So these proteins might form some sort of depletion flocculation, or they could contribute to the flocculation of the fat structures, or they would not contribute to this flocculation.
So in a mixed emulsifier system, like a protein and a small molecule surfactant, you will get competition at the interface. And the small molecule surfactants typically will come into a patch or a region on the fat droplet interface and then start expanding from that patch. And so it's going to depend to some extent on the ratio of the two surfactants in terms of how much displacement that you would get. But if you recall earlier in my presentation, I showed some micrographs where you see patches, almost what looks like a bare patch, and then a region on the fat globule where you might still get a patch of adsorbed protein. And so they're not going to form a homogeneous mixed layer. They're going to form more of a heterogeneous mixed layer. And that can, as you say, promote some instability in some cases. So you always, depending on the other components of the system, you always need to find the right balance between addition of a small molecule surfactant and the net effect that it has on your fat globules. I have seen instances where addition of small level of surfactant causes instability where people thought it was going to enhance stability. They thought, oh, just add a little bit of an emulsifier, that's going to help. But if it causes these heterogeneous patches to form, then that could cause instability, as you mentioned, like a depletion flocculation type of a process. So it always is a bit of trial and error when you start looking at new emulsifiers in terms of how they're going to behave in a protein stabilized emulsion, or likewise different mixed proteins and how they're going to behave. So you can do some a priori predictions, but quite often you need to back that up then with pilot plant trials or laboratory trials to find out exactly what the outcome might be.
Thank you. And finally, we have the last question, and is that, do you think that's feasible, the use of Pickering emulsions in food?
To well,
To use
to
Pickering emulsions in food, is that
oh yeah,
feasible?
oh yeah, absolutely. There's lots of cases of food systems where the major stabilizing force is a Pickering type emulsion. Um, there was a review paper a few years ago written by Derek Rousseau, who is a Canadian colleague of mine, on Pickering emulsions in food systems. It's not an area that I would consider myself an expertise on, but the answer is certainly yes, that emulsifying or that stabilizing force is one that is demonstrated in lots of different food systems.
Perfect. Thank you very much, Professor. Let's see, we have some other question. Nope. So thank you very much for the lecture today. It was a very, very comprehensible and a very understandable presentation. And it was very enjoyable too. Thanks.